Hello and welcome to Electronics. My name is Fatima Garba Yusuf, and today we are going to explore another aspect of phase diagrams, that's the determination of phase composition. In the previous videos, we've talked about an introduction of what phase diagrams are, what phases are, the different types of phase diagrams, unary phase diagrams, binary phase diagrams, ternary phase diagrams, all named based on the number of phases they depict. We've also talked about the calculation of the degree of freedom, as you will see in the videos we recorded earlier. So here we are going to focus more on the multi-phase diagrams, that's those phase diagrams that have more than one phase. And if you have noticed earlier, you will see that actually there's quite a distinct difference between the unary phase diagrams we looked at and the binary phase diagrams. This is because when you look at a unary phase diagram such as the standard water phase diagram, you'll notice that it has pressure on the y-axis with temperature on the x-axis. As for the binary phase diagram, it has temperature on the y-axis with concentration or composition on the x-axis. It's usually weight composition in percentage. So it is important to note that when we're talking about the determination of phase composition, of course you won't put the unary phase diagram into the picture because it has just one phase. But when you have a binary phase diagram or one that has more than two phases, you might be posed a difficulty where you need to determine the percentage composition of a particular phase that is present. Or even if it is an alloy made of maybe 2 or 3 metals, you might need to know the particular percentage of one of the metals in a particular phase. So this is where this area comes in, and there's even a rule that is usually used called the lever rule, and we are going to explore it later on. Anyway, as an overview, we can say that the composition of phase components may be determined through a temperature concentration phase diagram. For example, you might be given a specific temperature, and with that you can be able to deduce the exact fractions of the components of an alloy at a certain ratio. For example, if you're talking about when the alloy contains 50% copper and 50% nickel at a temperature of maybe 1300, you'll be able to know exactly how much percent of nickel is contained in the liquid phase and in the other phase. However, you should note that usually only the percentage or only one component is displayed on the x-axis, but that is not a problem, because if, for example, you have just the percentage of nickel on your x-axis, for you to get the percentage of copper at that exact point, you simply need to subtract from 100. Understood? So there are basic steps you need to just follow when you're trying to determine the phase composition, and I itemize them as follows. When the conditions specified indicate that the alloy is in the L phase, then it simply means that in the other phase, which can be said to be the alpha phase, for example in a copper nickel alloy phase system, then it simply means that there's no concentration of the particular component under study in the other phase. For example, if you are studying nickel and the conditions specified indicate that at that temperature and at that specific composition the alloy is in the liquid phase, that is, there's no solid at all, then it simply means that your C alpha, that's your composition of nickel in the alpha phase, is equal to 0. And this occurs vice versa. When the conditions specified indicate that the alloy is in the alpha phase, it simply means that the composition in the liquid phase is equal to 0. However, When your alloy is in a two-phase region, that is, it is neither completely in the L phase or completely in the alpha phase, then you need to draw a tie line and then trace downwards for corresponding values of Cl and C alpha. Here in this case, none of them is 0, so you have to determine them. And in case you are wondering what a tie line is, it is an isotherm that connects phases in equilibrium. By isotherm, we mean a line that is depicting constant temperature. So let's look at this graphically. For example, in a copper-nickel binary system, if we are given a phase diagram with temperature on our y-axis and our composition on the x-axis, then if, for example, our component under study is weight percent of nickel, then if, for example, you are told to determine the composition at 1300 degrees Celsius, you are going to trace here. Let's say at this percentage that is here, which is similar to, let's say, 35%. So at 35% nickel. So your question might come in a way that, okay, at 35% nickel and 1300 degrees Celsius, what is the composition of your components, that's of both nickel and your copper? So for you to determine this, you can trace this, and this will be your point where these two intersect, right? So at this point, your alloy actually falls in the liquid section. So it simply means that your composition of nickel in the alpha phase is equal to 0. Likewise, if, for example, you are given a low temperature at still the same percentage of nickel, let's say at, if we take this to be 1180 degrees, so if you trace this, it's going to fall in the alpha phase, meaning the composition in the composition here in the L phase is going to be 0. However, if it falls in between at a medium temperature of, let's say, 1250 degrees Celsius, then if you trace this, it's actually going to fall here. It's neither completely in the liquid phase or nor in the alpha phase. It's in the phase where we have two phases, both the alpha and the liquid phase coexist here, and you can call this maybe L plus alpha or alpha plus L. So for you to determine the percentage of nickel in the liquid phase and the percentage of nickel in the alpha phase, you will have to then trace downwards. As you can see in this diagram, your Cl will be the percentage of nickel in the liquid phase, and your C alpha will be the percentage of nickel in the alpha phase. So from this diagram, we can estimate our percentage weight composition of nickel to be something like 32 weight percent, while in the alpha phase it's going to be something like 43 weight percent. Meanwhile, if you are also asked for the percentage composition of your copper, since from the graph this labeling is actually for nickel, then for you to get your copper, it's actually the reverse. Because there's 20% of nickel here, it simply means that there's 80% of copper. If this is 20% nickel, this is 20% copper. So for each percentage you get here, you subtract it from 100% to give you the corresponding percentage of the complementing alloy. That is if it is a binary system, since only two metals make up the alloy, right? So here you have 80% copper, here you have 70% copper, here you will have 60% copper, And for this one that you calculated, 100 minus 43 will give you 57% copper, and while for this one it will be 68% copper. And that's it. That's how you simply determine the composition of your different phases from a given binary phase diagram. So we'll meet in the next videos to derive our lever rule to actually know the weights composition of our different components.